Assalamualaikum, Madam Isadora. Today we would like to present our assignment for digital signal processing, which focus on windowing filter. Our presentation is compare the Hemming versus Han window and rectangular versus Kaiser window. This is our team members. My name is Nur Izazati binti Muhammad Zaini. Other members in our group Nur Shazwana binti Anwar, Muhammad Badrul Hakim bin Muhammad Azmi, Nur Fatihah binti Muhammad Sabri, and Amelia Ashikin binti Azlani. Next, our content is introduction, windowing filter, objective, methodology, Hemming versus Han window, rectangular versus Kaiser window, discussion and conclusion. For our assignment, we focus on spectral analysis in digital signal processing or DSP. Spectral analysis in DSP is commonly performed using the discrete Fourier transform or DFT and also the fast Fourier transform FFT. FFT assumes that the signal is infinitely repeating. However, in real application, signals are finite in length. Because of this, discontinue occur at the signal boundaries. Discontinue produce unwanted high frequency component which are known as spectral leakage. To reduce spectral leakage, window function are applied to the signal before performing FFT. Windowing helps to smooth the signal edges and reduce leakage. However, windowing also has an effect where side lobe level are reduced but the main lobe becomes slightly wider. This result in reduced frequency resolution. Next, windowing filter. We choose Hemming and Han window to make a comparison. The Hemming window is a cosine-based window. It is designed to reduce the nearest side lobe and it does not fully go to zero at the signal edges. This means the signal is smooth at the edges, but it is not completely cut off, which help reduce sudden change in the signal. In terms of characteristic, the Hemming window provide a good side lobe suppression. At the first side lobe is significantly reduced, which help to lower unwanted frequency component in the frequency domain. Because of this, the Hemming window provide a balanced trade-off between frequency resolution and spectral leakage, and making it suitable for many signal processing tasks. For the application, the Hemming window is commonly used in narrow band signal analysis. It is also widely applied in speech processing, where clear frequency components are required. In addition, the Hemming window is used in radar system to reduce interference from unwanted signal. Next, for Han window. Han window is based on a cosine wave. It is designed to touch a zero at both end of the signal block. By doing this, the discontinue at the signal edges can be eliminated, which help to smooth the signal. For characteristic, the Han window is provide good side lobe roll off. This means the side lobe level decrease smoothly, and helping to reduce high frequency leakage in frequency domain. However, the Han window has a wider frequency response compared to the rectangular window, which means the frequency resolution is slightly lower. For application, because of these properties, the Han window is commonly used for general spectrum analysis. It is suitable for continuous signal analysis where smooth frequency behavior is important. The Han window is also used in noise measurement as it helps reduce leakage from unwanted frequency component.
Next, I will present rectangular window and Kaiser window. For definition of rectangular window, it is the simplest form of windowing, effectively representing the raw signal with no modification. Mathematically, it applies a weight of 1 to all samples within the observation period and 0 outside of it. Characteristic of rectangular window: it provides the narrowest main lobe, yielding the highest possible frequency resolution. However, because it preserves the abrupt discontinuous at the signal edges, it suffers from severe spectral leakage characterized by slowly decaying side lobes. Application of rectangular window. It is best suited for analyzing transients that fit entirely within the window or for separating signals with very closely spaced frequency where amplitude accuracy is secondary. For Kaiser window definition, it is a unique among standard windows because it is a parametric family of windows based on the zeroth order modified Bessel function of the first kind. It includes a tunable parameter, beta, characteristic of Kaiser window. The beta parameter allows the user to control the precise trade-off between the main lobe width and side lobe attenuation. By increasing beta, the side lobe levels are reduced at the cost of a wider main lobe. This flexibility allows the Kaiser window to approximate the performance of many other windows. Application of Kaiser window. It is highly valued in finite impulse response (FIR) filter design and high precision spectral analysis where the specific leakage characteristic must be customized to the signal requirements. So here is our objectives. First, to analyze and compare the performance of different windowing filters used in digital signal processing. Secondly, to demonstrate the characteristic and difference between Hamming and Hahn windows as well as rectangular and Kaiser windows in FIR filter design. Thirdly, to investigate the effects of window selection on frequency response, spectral leakage, and output signal performance using MATLAB simulation. Next, to apply the windowing method in FIR low-pass filter design, spectral analysis, and signal processing. Lastly, to develop an understanding of how windowing filters influence signal quality and filtering performance, and the importance of selecting an appropriate window function for specific application.
Next is methodology. Number 1 is signal generation. A test signal was generated in MATLAB. The signal consists of two sinusoidal frequencies, low and high frequency. The sampling frequency was selected according to the N-squared criterion. Number 2 is window function application. 4 window functions were used. Number 1 is rectangular, number 2 is Hamming, number 3 is Hahn, and number 4 is Kaiser. Each window was applied to the signal in the time domain. Distance reduced, age discontinuous, and spectral leakage. Number 3 is FIR filter design. FIR low-pass filter were designed using the window method. The same filter order and cut-off frequency, 1 kHz, were used for all windows. They ensure a fair comparison between window functions. Number 4 is frequency response analysis. Frequency response were obtained using MATLAB. Magnitude plot were analyzed to observe main lobe width, transition band, side lobe attenuation. Comparison were made between window pair. Number 5 is spectral analysis. First, Fourier transform was applied to the window signal. Frequency spectra were analyzed to evaluate spectral leakage. Side lobe level were compared for each window. Number 6 is output signal evaluation. FIR filter were applied to the test signal. Output signal were observed in the time domain, and signal smoothness, ripple, and noise suppression were compared.
Hello, hi, my name is Muhammad Rakim Rahman Azman. My matrix number is B122310128. Today, I will present about the BERT3373 digital signal processing assignment. So, this is present about the windowing filter application. I will present about the comparative analysis between two popular window functions. It's about Hahn Hemi, and the hand window. Okay, so first I will present about the first figure is all about the frequency response analysis. Okay, in this picture we can see the two different color of the line. So the red one, the blue one represent the humming window, and the red one represent about the hand window. Okay, in this figure we see the three conditions. It's about the pass band, transition, and the stop band. You can see if we go into deeper in this figure, we can see at the first band section, transition, at the first band section, we clearly can see 0 to 1000 Hz at the cutoff. Two both filters are successfully passed. Second, at the transition, we can see at the 1000 Hz, the both filters are sharply drop off. And the last one, at the stop band. Okay. For the stop band, uh, if you look closely at the explanation, the Hemi window blue line generally keep the first side lobe lower than the high window. However, the high window ripple decay faster as the frequency increase. Okay, for the second figure is about the spectral analysis. What is spectral analysis is to see how this window handle the signal. Okay, I generate test two conditions. First one is about the desired signal at the 500 Hz, and the second one is the noise signal at the 2000 Hz. Okay. In this plot, you can see the main lobe of the window. Both windows accurately identify the signal peak. However, notice the width of the main lobe and the height of the side lobe. The humming window provides the slightly flatter slope, while the high window is smooth at the edge. The comparison is when detect a weak signal in the presence of the strong noise. Okay, the last the third figure, are showing out the filter result or output signal plot. Okay, in this figure, we apply the filter to the space signal. The original input was made into 500 Hz and 2000, and the next signal like 2000 Hz. Okay, since our cutoff is 1000 Hz, the filter should remove the 2000 Hz noise entire. Okay. Uh, yeah, okay. You can see, you also can see the jet noise from the 2000 Hz component has been successfully filtered out by both the Hemi and the hand filter. The two, the two lines, red and blue line, are perfectly overlapped, providing, provide that to the specific application both window perform excellently. Again, okay. For this part, I will show you. I will explain about the coding and the process. First, let's look at the methodology I use in Snapchat. You can see the project and the process begins initially our environment. Okay, first we set the sampling frequency as of 8000 Hz, and the cutoff frequency is 1000 Hz. We are using the filter order in value 51. We calculate the ideal impulse response using the same formula. This is represent the critical perfect low pass filter. Okay, so uh, because we cannot implement in infinite filter in Unity, we must bracket it. So this is where the Hamming and window come. We apply the mathematical windows to our ideal coefficient. Finally, we generate a Nernst signal and apply to the filter. Use the fast Fourier transform to analyze the frequency and spectrum. This to compare the result because we want to compare the result. Okay. After that, uh, in the head of the design, FIR filter, we calculate the ideal impulse response. This idea in the HP theoretical, the impulse response of the ideal low pass filter is a sin function. Okay. The problem in this function is extend to the infinity. If we just chop it off using the rectangular window, we can get the Reef phenomena, which cause massive ripple in our signal. Okay. So we use the Hamming window, which is optimized to minimize the nearest side lobe. The hard lobe, which touch zero at the end, and generally offer the fast roll of the side lobe. Okay. Okay. For this slide, I will present about the rectangular window and the Kaiser window, where we are choosing two filter windows. Okay. To ensure the fair comparison, I still using the sampling frequency is about 8,000 Hz and the cut off frequency 1,000 Hz. Also that filter order we using a 51. So for the Kaiser window, I use a beta value of C. And this is crucial parameter because unlike the fixed rectangular window, the Kaiser beta allow us to tune the trade-off between the main lobe wide and the side lobe explanation. I calculate the window coefficient using the Bessel modified Bessel function of the first kind in MATLAB. You can see in the code. So this second figure, I will explain about the frequency response analysis. You can see the black solid line is the rectangular window and the green dashed line is the Kaiser window. Okay. For the two major observations, we can see the transition width and the stop band attenuation. For the transition width, we can notice the rectangular as a steppered roll off at the 1000 Hz. This is the main advantage of the rectangular window to provide the narrowest transition band. So the second one about the stop band attenuation. Um, you can see the ripple in the stop band after the 1000 after 1500 Hz. The rectangular window has a poor attenuation. Its the side lobe are quite high, around the negative 13 dB. In the contrast, the Kaiser window, green line, sacrifice a little bit steepness, but they provide significantly better attenuation. Dropping quickly below about negative 60 dB. This means the Kaiser filter is much better at blocking unwanted frequency. Okay, so the last one is will display the spectral analysis. Okay, when at the spectral analysis, we are using the FFT. I generate a test signal contain 500 Hz desired wave and 2000 Hz noise. Okay. So the main lobe we can see 0 to 500 both window accurately capture the signal energy. But the side lobe in the lead stage look closely like a skirt of a plot. The black line rectangular has a high side lobe that extends across the spectrum. This is known as a spectral lead. So the last one about the green line geyser suppress the side lobe much more effectively. Much more effective. This confirms that the geyser window intrudes less leak into our analysis than a primitive rectangular window. Okay. So about the output signal plot, uh, we can see the time normal result after filtering. The input was missing 500 Hz and 2000. Then our cutoff is 1000 Hz. So the noise should be removed at the 2000 Hz. So you can see the both rectangular and the Kaiser filter successful cleaned by the signal. Leave the smooth uh, in 500 Hz value sandwich. The line overlap almost perfectly because the noise frequency at the top at 2000 Hz was far enough into the stop band. Even the rectangular window for attenuation sus, was sus, was sus, sorry subsi- so subsequent so, sorry sufficient sufficient to remove it. However, if the noise were close to the cutoff frequency, the cancel window would like have more better perform. Hello, hi. For this session, you can see the project and the coding area. So, this coding, this figure is about full coding in MATLAB software. The right, the right side is about project diagram. So I compare the rectangular window and the Kaiser window to see the impact of filter performance and signal purity. Okay. So I start sampling frequency at the sampling frequency at 8000 Hz and cut off frequency at 1000 Hz. I calculate the ideal impulse response using the same formula. This is critical step. I apply the rectangular window and the Kaiser window. Finally, I generate a test signal with noise and analyze the result using FFT and time domain filtering. So moving forward, you can see using this coding, showing the black line is a rectangular window and the green dash line is a Kaiser window.
Hi and Assalamualaikum. My name is Nur Shazwana binti Anwar. My batch number is B122310502. In this section, we discuss how different window functions perform by comparing their edge shapes, spectral leakage and suitability for different types of signal. Hemming window has a smooth cosine edge shape and produces lower side lobes, resulting in less spectral leakage and a cleaner stop band. It is suitable for voice and speech signals. Hind window also has a smooth cosine shape, but it has a wider transition band and higher leakage compared to the Hemming window. This makes it more suitable for audio and music applications. Rectangular window has a flat shape with sudden drops at both ends, which give a sharp cut-off but causes high side lobe levels and strong spectral leakage. It is commonly used for test tones or synthetic signals. And lastly, Kaiser window. Kaiser window has an adjustable smooth shape controlled by the beta parameter, allowing very low side lobes and minimal spectral leakage. It is well suited for high quality audio applications. In this conclusion, this project successfully analyzed and compared different window filters using MATLAB. Results show that each window function affects frequency response, spectral leakage, and output signal quality differently. Hamming and Kaiser windows reduce spectral leakage and produce smoother output signals. Rectangular window has a sharp transition but causes high spectral leakage. Overall, choosing the right window function is important for achieving good signal quality in DSP. That's all for our assignment presentation. Thank you.